Welcome to Physics Lab Podcast. I'm Amara, and today we're exploring one of the most fundamental principles in physics, conservation of energy. We'll be examining how this principle applies to roller coaster dynamics and what happens when theory meets experimental reality.
Thanks for having me, Amara. I'm Marcus. Conservation of energy is fascinating because it tells us that energy cannot be created or destroyed, only transforms from one form to another. In a roller coaster system, we primarily deal with two types of mechanical energy: potential energy and kinetic energy.
Exactly. Let's break this down. Potential energy, or U, depends on an object's height above a reference point. The formula is U equals mgh, where m is mass, g is gravitational acceleration at 9.8 meters per second squared, and h is height in meters. When a roller coaster car sits at the top of a hill, it possesses maximum potential energy.
And kinetic energy, K, is the energy of motion. The formula is K equals half mv squared, where v is velocity. As the car descends the hill, potential energy converts into kinetic energy. At the bottom, the car moves fastest and has maximum kinetic energy, but minimum potential energy.
The total mechanical energy, E equals U plus K. In an ideal system with no friction, E remains constant throughout the motion. This is the conservation of energy principle. However, real roller coasters experience friction and air resistance, which dissipate energy as heat.
That's where experimental methodology becomes crucial. In our lab, we used photogates, sensors that detect when the roller coaster car passes through specific points. These devices measure velocity directly, allowing us to calculate kinetic energy at different positions.
Our experimental setup included measuring heights at 5 distinct points: the initial position, the top of the first hill, the bottom of the hill, and additional points around a loop. We recorded height values like 0.32 meters at the initial position and 0.9 meters at the top of the hill.
The velocity measurements were equally important. We recorded velocities of 0 meters per second at the initial position. The car starts from rest, and 16.5 meters per second at the top of the hill. At the bottom, velocity reached 1.96 meters per second. Wait, that seems counterintuitive. Shouldn't velocity be highest at the bottom?
Great observation, Marcus. That discrepancy highlights the difference between theoretical predictions and experimental results. Theoretically, if we assume no energy loss, we can calculate expected velocities using energy conservation. mgh1 plus half mv1 squared equals mgh2 plus half mv2 squared. The mass cancels out, simplifying our calculations.
So the experimental velocity being lower than theoretical predictions indicates energy loss. This is where friction enters the picture. The roller coaster track, wheels, and air resistance all dissipate mechanical energy. Our job as experimentalists is to quantify these losses.
Precisely. We calculated total mechanical energy at each point using E equals mgh plus half mv squared. Comparing theoretical total energy, which should remain constant, with experimental total energy reveals energy dissipation. The difference between theoretical and experimental values represents energy loss to non-conservative forces.
One particularly interesting aspect of roller coaster dynamics is the loop. For a car to successfully complete a vertical loop, it must have sufficient speed at the top to maintain contact with the track. At the loop's top, both normal force N and weight mg point downward, providing centripetal acceleration.
The minimum condition occurs when normal force equals 0, so mg equals mv squared over r, giving v equals square root of gr. For a loop with radius r equals 0.12 meters, the minimum velocity at the top is approximately 1.08 meters per second. Working backward using energy conservation, we can calculate the theoretical minimum initial height needed.
Our experimental data showed a theoretical minimum initial height of approximately 0.41 meters for the 0.12 meter radius loop. However, experimental results often require slightly greater heights because of energy losses. This difference between theoretical and experimental minimum heights quantifies real-world inefficiencies.
The experimental methodology we employed demonstrates how scientists validate theoretical models. We didn't just accept the conservation of energy principle. We tested it systematically, using precise instruments like photogates and careful measurements of height and velocity.
This approach reveals something crucial. Physics isn't just about memorizing equations. It's about understanding how real systems deviate from idealized models and why. Energy conservation remains valid. The missing energy didn't vanish. It transformed into heat through friction.
Students often ask why we bother with experiments if we already have theoretical equations. The answer is that experiments teach us about real-world complexity. They show us where our assumptions break down and how to account for factors like friction, air resistance, and measurement uncertainty.
For anyone conducting similar experiments, remember several key points. First, calibrate your photogates carefully. Timing errors propagate through velocity calculations. Second, measure heights from a consistent reference point. Third, repeat measurements multiple times to reduce random errors.
Additionally, consider sources of systematic error. The roller coaster car's mass affects potential energy, but cancels in energy conservation equations unless friction depends on mass, which it often does. Track irregularities and wheel alignment also influence results significantly.
The beauty of studying roller coaster dynamics is that it combines fundamental physics principles with practical engineering considerations. Understanding energy conservation helps engineers design safer, more efficient rides while minimizing energy waste.
As we conclude, remember that conservation of energy is one of nature's most powerful principles. Whether analyzing roller coasters, pendulums, or planetary motion, this principle provides insight into how systems evolve over time. Thank you for joining us on Physics Lab Podcast.
Yes, thanks for listening. Keep questioning, keep experimenting, and keep discovering the physics that surrounds us every day. Until next time.